All right, guys, hopefully you can see this on the notes of the paper. I want to go over some misconceptual questions with you guys just to review some of these things, and then we'll get to the end of this section of notes in this right now, I think. Q1 is negative 0.1 microcoulomb. It's located at the origin. Q2 is positive 0.1 microcoulomb. It's located on a positive x-axis at x equals 1 meter. Which the following is true of the force of Q1 due to Q2? So, Q1 would be attracted in the positive x direction, right? It's going to be attracted to it. And the way that I drew this, if that's 0, and that's 1. Swap positions of Q1 and Q2, which define as truth of the force on Q1 due to Q2. If I flip these, Q1 is now going to be pulled in the opposite direction. It's always going to be pulled towards the other charge. Fred the lightning bug has a mass of m and a charge of plus q. Jane, his lightning bug wife, has a mass of 3/4 m and a charge of negative 2q. Because they have charges of opposite sign, they are attracted to each other. Which is attracting more to the other and by how much? You would use the same equation to determine their force of attraction, right? So this is, do you pull on the earth more than the earth pulls on you? The answer is no. So these are action-reaction third law pairs. So they would be attracted by the same amount. Are you guys lightning bug or firefly people? I think I was a firefly. We called them fireflies when I was a kid. Figure 1650 shows electric field lines due to a point charge. What can you say about the field at point 1 compared to the field at point 2? Yeah. The closer you are to the charge, the bigger that it is. So it doesn't matter that you reside on a field line or not. The electric field is how closely they're bunched together. So D is our best answer. 5, a negative point charge is an electric field created by a positive point charge. Which of the following is true? The field does not point towards the positive. No. That one's not right either. It's going to be D. The field points away from the positive. That's the way they point. And the force in the negative would be opposite. Yeah, because the field's defined as what a positive point charge would feel. And we're saying that it's in the opposite direction. As an object acquires a positive charge, its mass usually, I don't know what they want. If you're acquiring a positive charge, you're losing electrons. So I guess you could say your mass is decreasing, but it's so small. So I would say, electrons have mass, I guess. I'm not sure what they want there. I don't have... I don't care about either one of those. 9, we are usually not aware of the electric force acting between two everyday objects because it is weak. It's much smaller, much stronger than gravity. It is not because to deal with that or that it's invisible. It's that most things have the same amount of charge, positive and negative. To be safe during the lightning storm, you're better inside of a metal car. And I don't even like the metal. I don't even like the car example. I like the railroad car example because everything's metal inside a railroad car, and you're still safe. Because inside the car, there's plastic things. You have rubber tires. People get confused. Which vector best represents the direction of the electric field to fourth corner square due to the three charges shown? This one would push it down. This one would push it out. This one would pull it that way. But these two together would cancel that out. So our best answer is D. So our electric field inside of a conductor is 0. The charge on a conductor is going to stay on its surface. And I'll show you guys a couple demonstrations with that as well. Or we actually, depending on when you're watching this, you've already seen it. So that's how I could dissect the Leyden jar and not get shocked. Electric fields are always perpendicular to the surface. All right. Which of the following is true about the net force on an uncharged conducting sphere in a uniform electric field? If its net charge is 0, its force would be 0. So even though it's made up of charges, they would balance out. So we have a hollow metal sphere everywhere inside. This is 0. So we have 0. We have 3/4 R. The electric field 0 at both these places. We have 5/4 R. And we have 2 R. This one is closest to the surface, but not inside. A positive charge of 10 to the negative 6 coulombs is placed on insulating solid conducting sphere. Which of the following is true? We don't know this yet, but the reason why charge flows is because of unequal potential. So charge is always going to flow in conductors until the potential is equal. This is going to be the science behind how a battery works. All right, so this is from your book, which is supposed to be based off of the AP. Scroll this down. All right, we have two kinds of electric charge, completely arbitrary. It was Franklin explaining the Leyden jar problem, and he explained it in terms of bookkeeping, where you could be in the positive or in the red, but everything has to account for itself at the end. Charge is conserved. So the amount of charge in a system isn't created or destroyed. It'll just look different, but it's the same. So the kind of problem you would see with this is if you had two conducting spheres. One has +8. One has -5. You transfer some charge from one to the other. What would be possible combination? So the total amount you have can't change. It can be in different places. So in this case, I have plus 8e and minus 5e. E is our elementary charge. All charge is made up of combinations of E. So right here, I know that I have plus 3e. That's the net charge I have. I can't have more or less. It can be in different places. So my first one here, does this match up? Did I conserve my charge? Well, I have plus 2e and minus 3e. That's a negative e. That's not possible. I lost 4 charges there. Here I have a plus 3e and a negative 1e. I have a plus 2e. I had a plus 3e, now I had a plus 2e. This isn't possible. I lost a charge somewhere. I can't. It has to be conserved. Negative 4 or plus 4e minus e added together would be plus 3e. This one agrees with that. Charge is conserved. So it's possible that it went from there. And then finally, plus 6e minus 2e would be plus 4e. And that also would be possible. So those are AP problems show up like that. Conductors move freely on, electrons charge moves freely on a conductor and it resides on the surface. It wants to get as far away as possible. Inside, I am safe. Things that do not allow charge to flow are non-conductors. Charge is quantized. So that means that you could only have 1, which is 1.6 times 10 to the negative 19th, 2, which is 3.2 times 10 to the negative 19th, 3, which is 4.8 times 2 to the negative 19th. We can charge things by conduction, which is touching, or induction, which is non-touching. So I showed you that with the metal spheres. The force, and again, electrostatic force is a Coulomb's constant, Q1, Q2 over R squared. And again, you'll see this in the lab you do, but they use a torsion balance to measure this. The electric field is a way to explain what's going on, and it is the force per unit charge. It is just like we did gravitational field strength. Another word for gravitational field strength is acceleration due to gravity. We just cancel out, factor out a mass. You don't need to know these formulas. That doesn't show up in the AP test. But the fields are important because they're going to lead to the potential and the potential energy. And I would be amiss to not talk about electric potential energy because energy is the thing that connects all this stuff. So I don't know why AP decided they were going to talk about force and not energy, because it's this transfer of energy from all these different forms that kind of unifies our entire discipline of what we study. So our electric field inside a conductor is going to be 0